how this is a good example to see how agent-based modeling can meet empirical data. Yeah, and the techniques that I introduced today can be also used to simulate other collaboration networks. We have, for example, papers where we model the collaboration of scientists in writing publications in the very same way as we model the collaboration of firms. So we are interested in economic networks for quite some time. In 2009, we wrote 2 papers where we tried to address the problems and the challenges when you model economic networks. There are 2 different perspectives that you have to bring together. One perspective is the perspective of the economist who thinks of the strategic behavior of a firm. The major question for the economist is the why question. Why do firms engage in collaboration? What do they gain from doing this? So that means we have to think of the strategic dimension of a collaboration. Whereas computer scientists or data scientists ask the how question. So how do firms collaborate? What type of network structures do we see if we look into large-scale data sets? And we try in our group to bring these 2 perspectives together. We have data on the one side that we analyze, and we think of strategic interactions of firms on the other side. We have studied different types of economic networks in the past. So, for example, we studied financial networks. We were interested in systemic risk. So that means the type of relations between different economic actors, for example, banks here in the US, is associated with some risk. What you see here is a network of OTC derivatives, over-the-counter derivatives. These are contracts that firms subscribe with partners, and they don't tell about this. So that means they only tell us about a exposure, a general exposure that they have to report every quarter. But we will never find out about the contracts themselves and the partners. So what we did is in this network paper, we try to extract those hidden relations between different banks. And everyone should be interested in this, because if Bank A has a relation, a contract with Bank B, but also a contract with Bank C, then Bank C will affect it if Bank B gets bankrupt, for example, because this will affect the central bank, and the central bank, the Bank A, will pass this shock on to Bank C. And this is important to know in order to get an idea about systemic risk. That's a network that no one knows, but we have extracted it from data. This is another example of ownership networks. So we have about 40 million firms on Earth where we know about data of their ownership. So it means firm A owns 20% of firm B, and firm B owns 15% of firm C. That means that firm A has an indirect control over firm C via firm B. And you can anticipate that this makes a huge network that is spanning over the whole globe. But the interesting thing is that most of this network is not interesting. What is interesting is the core of the network. The core of the network is very, very small. Only 1,300 firms make the core of the worldwide ownership network. And they are tightly knit to each other, as you can see in this picture. So in this small core, every firm owns every other firm in some way. So that means what we see here is a picture of the heart of the global economy that has about 20% of the total production of all of the world economy is concentrated in this. And we have analyzed these type of structures to find out about the influence that firms can have. And this is our example of today. It's about collaboration networks. We have analyzed a data set of about 15,000 firms that have collaborations with other firms over a period of 25 years. In total, these firms were engaged in about 21,000 different collaborations. We know about this because you have to sign a contract if you engage in these type of research collaborations, and we have analyzed this data. I show you a small picture, a small video afterwards, but just when you look here into the structure of these networks, then you see that these R&D networks follow a life cycle. In the beginning, you see there is almost nothing. Then you see two strong clusters emerging. The color of these clusters indicates the different industrial sectors in which these firms have their main business. And in our case, this is pharmaceutical and computer engineering. And then you see that these clusters disappear. Why do the clusters disappear? I said in the beginning that firms need to have a reason to collaborate with other firms. So there is the why question important. And once firms have collaborated for a couple of years, so then they found out that they have exchanged all their knowledge. Why should they continue to collaborate? Collaboration is a costly endeavor for a firm. And that's why we see that this network disappears. Let's have a look into our small video here. That's okay. So I do hope that everyone can see this. So we see that firms from the data set emerge on the scene, and these firms form research collaborations. And this way you see the network emerging. The network becomes denser and denser, and you see clusters of red and blue firms. This is because they belong to different industrial sectors. But if you watch this long enough, then you see that this network disappears again. Why? I explained it. The firms have basically exchanged their knowledge and they cut costly collaborations and start a new business. So that's the visualization of this. We want to understand this life cycle behavior from the different perspective. We have started two different directions. One direction comes from theory. I'm not going to talk about this today. There we have quite abstract models about link formation of agents. Each agent is a firm, and then this firm is characterized by a utility function, and in order to gain a positive utility, firms decide to collaborate. But then they carefully check whether they should collaborate with firm A or with firm B or with firm C, because they want to maximize their utility or their profit from this. So this is what we mean by strategic link formation. How much information has a firm available when it creates a link? How long will the link last? When will the link disappear? We have published a number of rather abstract and mathematical papers about this subject, and you can take a look here into these publications. You find everything on our website, and there are also links to the PDFs if you are interested. The second direction was about empirics. As I said, we have quite a bit of data available, and we wanted to look into a characterization of these networks. Why is it that they have this life cycle, that the network first is formed and then disappears again? What are the major players in this network, and so forth? So we have published also papers on this empirical analysis. You find it on the website, and in the following I show you a few small glimpses of the results. So one result is about heterogeneity. What does this mean? Heterogeneity refers to the number of partners that a firm has in this collaboration network. There are many firms that have only 1 or 2 or 3 other partners and with whom they collaborate, but there are a few firms that have 50 or 100 different partners. This is expressed here in the so-called degree distribution. Degree measures the number of partners that a firm has. And what we see here is a probability distribution. So this gives me the number of firms that have a degree of 50, for example, or the probability to find such a firm. And you see that this is a very broad distribution. That means that firms that have very many partners cannot be ignored in this data set, even that we have 15,000 firms there. We can characterize these type of distributions, and so the table gives some results about this. The other example that I want to give here is about assortativity. What does this mean? Assortativity means if I have a small degree, that means I have only a few partners. What is the degree of my partners? If I am a small firm with a few partners and collaborate with another firm that also has only a few partners, then this is called assortative behavior, because nodes with a small degree connect to each other, and load with a large degree also connect to each other. That's called assortative behavior. Nodes with similar degree are connected. And we see this indeed for firms that have a small degree. But for firms that have a large degree, like here, we see dissortative behavior. What does it mean? It means that the Samsung company is not collaborating with the Toshiba company, which is another big player. It means that the Samsung company is collaborating with a large number of very small companies. And the Toshiba company is also collaborating with small other companies. So that means this picture reflects the fact that the big players do not collaborate in research collaborations. Instead, they collaborate with startups and small companies. And it is interesting to see that when firms start, so they have this assortative behavior. That means they connect to similar firms, whereas once they have grown up, they start to collaborate with smaller firms. That is a very interesting finding. Then we have looked into 2 other measures that we later use for our simulation. That's why I write input here. We looked into how many collaborations do firms have in a particular time interval. And you see the same broad distribution here with respect to the activity. So this is a double logarithmic plot here, as you see. And we have a very broad distribution here. What does it mean? It means that most of the firms only engage in 1 or 2 collaborations at the same time. This is here measured over time. But a few of these firms engage in very many collaborations at the same time. That is what we see here. And we use this information about how many collaborations has a firm in a given time interval later for our simulations. The second measure that we evaluated is the size of the collaboration. The size of the collaboration means how many firms collaborate together. I collaborate with you, and you collaborate with another firm, and this firm also collaborates with me. So we have a small cluster of 3 firms that collaborate. And here we measure this collaboration size. How many firms form such a cluster or such an alliance? And what we see here is, again, this very broad distribution that we find all the time. Most firms have only 1 or 2 are part of a cluster of very small size, but a few firms form very large consortia. We call this alliances or consortia of firms that collaborate for research and development. And this size of the cluster or of the alliance is also taken as an input parameter for our model. So now I shortly introduce to you our agent-based model. We would like to understand how firms enter this collaboration network, which is pretty big, well, with 21,000 collaborations. And we have developed a so-called label propagation model. So what type of firms do we have available? We make a distinction between firms that are already established, that means they have a history in their collaboration, and newcomers. These are firms, newly founded startups. So a firm that has already a collaboration before has from this collaboration a color. That's our label. Yeah, you can think of something very abstract if you want. And now this firm decides to collaborate in a new collaboration. The question is, if this firm has a green label, what's the probability that it will collaborate with another firm that also has a green label? What is the probability that it instead chooses a firm that has a different label, that means a different color here in our picture? Or what is the probability that it does not choose a firm with a label, but a newcomer? These are the newcomers here. So these are 3 different probabilities: same label, different label, newcomer. They sum up to 1, and we need to determine this. For the second group of firms, these are the newcomers. A newcomer never collaborated with anyone before. So the newcomer has 2 choices. It can collaborate with an established firm. So these are the firms here that have already a color, or it collaborates with another newcomer that also has no color. So that means I have 2 probabilities here with a not labeled firm and with a labeled firm. So because these probabilities sum up to 1, we only need to determine 3 independent probabilities. Yeah, in total there are 5. So how do we do this? We cannot use the calibration. For the calibration, we cannot use the full data because later we want to also do a validation. So what we take from the network, from the empirical network, is a few aggregated measures. I mentioned them here, average degree. So that means we take the huge network of 21,000 collaborations, and then we calculate what is the average number of links that one firm has. That's its number K. We calculate the average path length. That means how many steps do a firm need to take before it reaches an arbitrary firm in the network. And we calculate the global clustering coefficient. The global clustering coefficient calculates the number of triangles. Yeah, so firm A and firm B collaborate, and firm C is also there. So that means if A and B collaborate, so what's the likelihood that C and B also collaborate? That's measured by these triangles. And we take from the empirical network only these aggregated numbers, and then we run our agent-based model and try to match with our simulation these aggregated numbers. That means we are not completely fitting the model. We are just making sure that an aggregated measure of 100 is met by our simulation with another aggregated measure of hopefully 100 or a little bit less. So, yeah, so there's an error, and then we get here an area where these three different probabilities, the independent probabilities that we wanted to measure, are very close, give very close results to these aggregated measures. Then, if we have these probabilities, we can now run the real agent-based simulation. And what you see here on this, in this part of the table, are these 5 probabilities that we have just determined. So we did this for the different industrial sectors. This is the area in which the firm is active, for example, pharmaceutical or computer software and so forth. And these numbers can be interpreted. For example, we can look into this number here and this number, and they together sum up to more than 70%. What's the meaning? It means if you are an established firm, then you prefer to connect to another established firm. You do not prefer to connect to a newcomer, for example. This is what we can see here. So the other number that we see here, if we compare these two numbers, is that firms prefer to connect to those firms that have the same label or the same color in our simulation in comparison to firms that have a different color. So that's also interesting. And for the newcomer, we see that the newcomer is mostly interested to collaborate with a firm that is already part of a network instead of another newcomer, for example. So these are very interpretable results with respect to these probabilities. And now we come to basically simulate this network dynamics. I only show you this one slide. If you are interested in more validation measures, I recommend you to go to the paper. So we have like 5 or 6 different measures of this. And what you have to compare here is the blue dots, which are the simulated networks, with the yellow dots, which are the empirical values. So we see 4 plots here that characterize the networks in different dimensions. And the remarkable thing here is that in all of these cases, you see that the yellow dots and the blue dots are very close to another. That means we have a model that is very, very well able to reproduce empirical findings. And these empirical findings have different meanings, as I said. So this is the number of partners. This is, for example, the triangles, the closed collaborations here. Component size means how large are the clusters that these firms form. And so this is a very positive result. As I said, you find other measures in our paper if you're interested in this. Here we have just reproduced also the different cluster sizes here. And we see that it well confirms with the empirical finding. I present this here because I want to convince you that we are able to reproduce results in different dimensions. This is not all the same type of results that you would get from fitting a model. So if you don't have the dynamics of the agent-based model right, then you would not be able to get to this. We looked into other interesting feature of this collaboration network. For example, how well firms are integrated. You can measure this integration by a so-called weighted k-core decomposition. I'm not going to tell about the details of this measure, but this gives you a number for every firm. And a number 0 means you are in the core. You are one of the most central firms. And a number of 17, that's the maximum that we found, means you are somewhere here. Yeah, so this is you, and this is the core. Yeah, so that's a measure to tell you about the integration of these firms. And now the most obvious question is, does this structural measure tell us anything about the success of the firm? Is a firm that is in the core more successful than a firm that is in the periphery? And therefore, we have made a correlation analysis where we looked into the output of these firms. I'm always talking about research and development activities. So we were looking into the number of patents here. And then we see that there is a very clear relation between this coreness value, which we have detected on the network, and the success of the firm in terms of the number of patents that they have produced. This is an interesting finding because the number of patents tells you about your performance, right? So, whereas this coreness value C tells you about the position of the network, in the network. That means we have a clear relation between your position in the network and your later success in these R&D activities. Good. If I have to characterize our methodology that we have used to develop these results, so then it usually starts here. We have macroscopic observations from the data. For example, the network that we have constructed from the data, and then the measures that we have calculated on this type of network, like mean degree and so forth. Then the next step are microscopic rules. These rules are not obtained from the empirical observations. These rules are proposed by us. So this was a picture where I told you what will a newcomer do, how will the newcomer connect to the network, how will the established firm connect to the network. So these are our hypotheses, how firms interact in this network. Then we implement these rules in large-scale agent-based model, and then we try to calibrate the 3 parameters that are in these rules. These were the 3 different probabilities that I have mentioned. This is calibrated here, and then once we have this, then we can use the fully calibrated model to reproduce other features of the system that we have not used for the calibration. I showed you this one slide where the blue dots match the yellow dots. This is our methodology. As I mentioned in the beginning, we also use the same methodology to address questions in social systems. Yeah, I wrote this feature article here about sociophysics to tell you about the possibilities that can be achieved in the modeling social systems with agent-based models. And one of our running example, I also mentioned this, is the collaboration of scientists, so where we apply this. So let me conclude. Our major interest is in collaboration networks. Why is this interesting? Because collaboration networks, as you have seen in this video, are very, very dynamic systems. So all the time, new firms enter the network, other firms leave, new collaborations are established, and so forth. So it's a very dynamic system. So I talked today about the R&D network with about 14,000 firms and 21,000 collaborations. But as I said, we also did this for scientists, where we have then 226,000 scientists and 1,500 different collaborations. Our modeling approach is an agent-based modeling approach. And what we see here is that we do not need to know all the details of the agents in order to get the systemic behavior right. Instead, we follow a probabilistic approach, as I introduced it today, with the 3 different probabilities. And this, as we found, is sufficient to model the behavior of the system as a whole. If you are interested in just a specific company, then you would not use this type of approach, of course. Yeah? So what are the new insights that we can derive from these type of investigations? We have a better understanding of whether the difference in firms makes an advantage or not. That's something that we could figure out in our study. So that's what economists call by the term heterogeneity. Heterogeneity means how different we are. And we found out that, that firms in their behavior are very different. Some have many partners, others have few partners, some are engaged in large collaborations, others in small collaboration. So there's a huge variety in this firm behavior. And once we have this calibrated model, then we can, of course, also try to basically influence the system. So I wrote here optimization. So we could, for example, provide firms with incentives to collaborate with firms of other colors in our simulation, and then see what is the impact of these type of incentives in order to get a more efficient structure or a more resilient structure. So this goes then into the direction of policy design, which is only possible after we have a model that is fully calibrated and has shown that it is able to reproduce empirical results. With this, I finish and look for your questions. Yeah, thanks for your attention.